Good evening. We're Kerbal, representing the IEEE Hardware Competition Robot. My name is Craig Ledbetter. I've got with me Paul Cosmopoulos, William Westbrook, Joseph Mills, and Roy Griffin. So tonight we're going to introduce you to our project. We'll review the project requirements and take a look at the competition course layout. We'll then have a quick video of us competing to illustrate the competition itself. We're then going to discuss our robot design, covering motion, aiming, and firing. We're going to delve into the chassis design, discuss our power system. We'll wrap up the design by looking at our methods for detecting the robot's start and stop. A little harder than it seems. Then we'll focus in on our accomplishments and some of our lessons learned. Finally, we'll summarize our experiences and field any questions. I'd like to hand off to Paul to start us off. Thank you.
Okay. Every year, IEEE Region 3 has a conference, which includes Southeast United States and some Caribbean countries. During the conference, they have different events, competitions, and a hardware competition. This year, the hardware competition, was to simulate a game of basketball. The requirement for this was the team had to build an autonomous robot that could operate through a course that simulated a basketball court. The robot followed a line, made turns, and there were 3 parallel lines that simulated a free throw line, half-court line, and a three-point line. Three-point line was a curved line on the course. Another requirement was that it had to finish in 2 minutes or less, and the points were based on completed time and starting, stopping, and accurate, successful shots. And every minute or every second finished under the 2-minute mark received a point. The course is a 4x8 sheet of plywood. It has a 12-inch square starting block. The first line, like I said, represents the free throw. The curved line is the three-point line, and the last line is the half court. The firing block is in the center of the course, 2 foot tall, with a 5-inch diameter hole in the center. We have a video of our performance at the competition. During this, it's also animated where it shows our points. We received 25 points for starting. We made a proper stop at the first stop block, which was 50 points. First dart made a successful shot with 300 points. The second line, we've had a proper stop and a successful shot for another 300 points. We did have a miss on the third shot, but we still received the points for making a proper stop on that block. After that, we made it to the stop block, which we received points for stopping properly, and we received 80 additional bonus points for finishing under the 2-minute time.
I'm going to run over the basic overview of the design for the robot. At the start of the project, we divided all of our tasks, the competition into separate tasks, and identified what subsystems were needed to accomplish the whole run. You can see at the top, we have our inputs. This is a very high-level view, by the way. Our inputs, such as the ultrasonic line sensor, ultrasonic distance sensors, and the line sensor. They're being fed into the microcontroller. We went with the Arduino Mega because it had quite a few number of I/O, digital and analog. And then down here we see the outputs from the microcontroller being fed to the different motor drivers and servo motors. We took a modular approach with all these subsystems. We had everybody in a leadership position, at least one subsystem, and a secondary role in others. This allowed us to accomplish many things at once without crawling all over each other, fighting for robot time. And it worked out well for us, I think. Key to this was communication at our meetings and trying to keep your hands in your own pie. And just trying to give little tips, but I think it worked well. One of my portion was like was emotion, drive motors, line following, PID control. And for this project, we went with the differential drive motor design. It's basically two motors, and we used a rear caster. Allows us to rotate in place. You have very tight turning radius. So if you need to make line corrections, you don't have to worry about turn radius issues and whatnot. We used very small but powerful brush DC motors. They're rated for 260 ounce inches of torque per motor, which is quite a bit for a little motor, and 120 RPM at 6 volts. The speed directional control is provided by the H-bridge, and using a PWM signal from the microcontroller. What this gave us was the ability to travel at 24 inches a second, and great acceleration from full stop in an inch and a quarter. So it accelerates very quickly. For the line following, we used a line sensor array. This consisted of, see here, let me check my notes. Line sensor array, as you all know, light reflects different on black surfaces than it does white. It has reflecting on white, and on black surfaces, the light is absorbed. So we were measuring reflectance using an IR emitter receiver pairs. Since we're limited on analog inputs, and we needed 8, and we had a bunch of other digital inputs, we used a pretty cool method of determining reflectance using RC time constant. Basically, we had a capacitor in series with a phototransistor, and the phototransistor, once the capacitor was charged, we set the digital output to an output and charged the capacitor, and then the phototransistor, whenever digital I/O was set to an input, we would just measure the amount of discharge time of the capacitor. This all happened in a very short period of time, so we had a good sampling time and allowed us to make adjustments. And ultimately, we used the different line sensor values in a weighted sum equation. I'm getting ahead of myself, I apologize. And fed it into a PID algorithm, which is this equation here. Rather than explain all this, I kind of sat around and was like, how do I explain this? Public speaking obviously isn't my strong suit. So I came with animations. I can do PowerPoint. So here we go. These are all purely fictional values. I just want to use an illustrated point. Right here we have the line sensor, and it's all the way to the left. And you see the PID output is very high once fed into the equation. And if we look down here, the left PWM this is our base speed. We have a little interface via an LCD. We can change this, and we can add the PID output. And the PID output is subtracted from the right. That's another reason why we went with the differential drives setup. And as the light sensor moves over, you can see the right PWM is going up. Now the PWM is constrained at from 0 to 255. And you still see the left drive motor is going full speed. So we're getting more of a correction now. There were less of a correction with the right motor PWM being greater value. And you see as the line sensor moves over, they're equaling out. And we have symmetry on the right hand side. I'm going to turn this over to Will.
Thank you, Roy. I'm going to go over the aim and firing mechanisms that we use. Our robot, we kept it simple. We used 4 ultrasonic sensors, 2 on the front and 2 on the back. The front 2, we used an average of 100 soundings. This allowed us to get a very accurate and waste some time because we had to be on the shop block for 3 seconds. So it allowed us to waste time productive. On the side, they're a different model, so they actually do internal averaging. So we didn't actually have to code it in to do the averaging. And with this said, we take the soundings and the averages, and we calculate the distance away from the outside wall and the wall to the target. And that's pretty much how we found our position on the board. Now, there is a fail-safe method that if a dart landed in between the side of the robot, it would be an obstruction and we would get an invalid reading. So we actually hard-coded it in with predetermined measured distance from the target to each shot block line as a fail-safe. So if we weren't in the range that we determined was a valid range, that it would just fall back to this code. Now once we have these distance measurements done, we use geometry and trigonometry to actually calculate the angles that we make with different walls and stuff, which I'll go in a little bit later in a diagram, which is right here. So the red dotted lines are the soundings that the ultrasonic send out, and then the green dotted lines are the calculated distance that we actually calculated. Now as you see that I put the robot off the line a little bit, so we actually measured the angle that the robot makes with the outside wall, and this we call the offset angle. We use the offset angle to actually calculate the angle that the pan needs to turn. If it's this way, we would add the offset, or this way, we would subtract the offset. And then we use the front soundings to actually get the distance to the target to determine how high we actually needed to turn the pan, or the tilt servo. Now, also in firing, we kept it simple. We used the internal parts of a Nerf Strike dart gun. We used their flywheel style motors and the magazine, and we used one servo for the actuation. Now, actually going through the sequence, once the robot stops and does its sounding, then the servo will sweep forward, pushing the dart forward, and once the actual flywheels, which are spinning really fast, catches the tip of the dart, it will actually pull it through the barrel. And then once this is done, then the magazine will actually push the next dart up because it's spring loaded. And I'm going to hand it back to Paul to talk about.
I'm going to talk about how we came up with the idea for this type of chassis. Doing some research, determining what we needed for the competition, we realized we couldn't find a custom chassis that was already built. So we had to custom design a chassis out of impact-resistant polycarbonate, and each layer was designed specifically based on components we needed for that layer. Starting with the bottom layer, we have the start sensors, stop sensors, and the line columns. Layer 2 has the motors, drive motors, the ultrasonic sensors, the Arduino microcontroller, 2 voltage regulators, and the battery pack, as well as the power bus. Layer 3 has the microcontroller, the pan and tilt servos, and the mount for the pan and tilt servo motor. The top layer has the magazine, the firing magazine, firing motors, and the servo for the firing sequence. The power requirements for this, once we did all our power calculations, we decided to come up with a 7.4 volt, 3650 milliamp hour lithium polymer battery. The battery feeds 2 10 amp voltage regulators. Each voltage regulator feeds a 5 volt power bus and a 7.4 power bus. The 5 volt power bus provides power to the Arduino microcontroller, the ultrasonic distance sensors, line following array, firing servo, pan and tilt servo, and the 7.4 bus provides power to the 2H bridges that provide power to the drive motors and the firing motors. I'll pass it over to Joe.
Thank you, Paul. For starting, we use 6 solar cells strategically located on the bottom of the robot to detect light from the LED in the starting block. It's an array of LEDs. The LEDs emitted such a low light that we had to use a large surface area, and that's the reason why we ended up going with the solar cells. The solar cells produce the voltage, 0 to 5 volts across an analog input on the Arduino. And the Arduino would then determine on boot, it would determine the ambient light in the room. And then from that ambient light, it would start taking measurements. And it would subtract off that ambient light, and if that value was over 1 volt, then the robot would start. For stopping, we used a snap action momentary switch, which was also mounted on the bottom of the robot. And as the robot moved over the 1/4 inch raised block, it would trigger, and that would cause a stop on the robot. We also use ultrasonic distance sensor, and this sensor was to measure if we got too close to the wall, we'd have a hard time turning around. And so if it went within 6 inches of the wall, the robot would stop and enter the aiming and firing routine. For the budget, the Team Kerbal originally estimated the budget to be $1,000. The overall budget that we ended up spending was right at $1,040, with $860 of that being for the components to build the robot, $81 being for the course material, and then approximately $100 for a spare kit that took the competition. The Citadel funded almost all of this, so thank you. This is not include the cost of the trip to the competition. So our helmet. The subsystem integration was completed on February 12th, and from that point on, we did not make any major adjustments to the robot from a hardware perspective. On February 26th, we finalized the software integration. So again, other than minor tuning, we didn't do anything else to the robot. On March 3rd, we finished the testing and validation of the robot, and from that data, we gathered that the robot completed the course in approximately 40 seconds. It completed the course 95% of the time, and it was accurate to about 70%. We could complete the course multiple times, over 8 times on a single battery charge. So to get setup, we had, as he said, we went to the competition and competed in the competition on March 14th. After the 3 competition heats, we were in first place. The top 4 teams went to the final round, where Team Kerbal finished 3rd overall. And I'm going to hand it over to Craig.
Thanks, Jim. I believe by Dr. Haynes standing that we are running short on time, so I'm going to run through this stuff pretty quick. What did we learn? Configuration management, big thing. We've got a big team, 5 people all working on different stuff at the same time, working on the same code base, dealing with documents all at the same time. So we went through and we produced a revision method, made sure all of our documents were labeled well, we knew what version people were working on. Anytime we made a modification to a document, we incremented the revision or a sub-revision, or made a major change, we communicated that to the team via email or a huddle and just said, hey, I made a big change, you guys need to update your stuff. That helped us integrate later much easier. Everybody was working off the same common code base. We integrated once. I couldn't believe that. We integrated code once and were able to proceed forward. Everything worked really well. Next thing on here for lessons learned, light and color sensors. They don't work very well. We initially started out with color sensors. We were going to find blue stop blocks on the course. We were going to stop when we saw blue. Robot was moving too quick for that. Refresh rate on the color sensors wasn't good, and the light was never really very good either. So as an alternative, joking with a snap action stop switch, we just decided to see what the 1/4 inch lip was on the stop blocks, and that ended up being good enough. For light sensors, the starting signal was the LEDs under the board lighting up. You couldn't start till they lit up. Well, we had a bunch of photoresistors underneath the robot. Now, we'll see the LED. Not really. We had to be precisely positioned over the top of these green LEDs to even see it. We hadn't hawed for a while. We brainstormed. We eventually decided we needed more surface area. Best thing to do with that, solar cells. Solar cells ended up working out fairly well. We weren't sure if they were. That was a last-minute change. Glad it did, because we would have been stuck never starting if we hadn't. Line following. Everybody can follow a line slowly. We saw that in competition. people did it a lot. Most people did it over 2 minutes. We did really well in competition, partly because the teams that were firing really accurately were doing it after the 2-minute time expired. Evansville, I believe, had that problem constant. Anyway, what we chose was a fast robot. We set everything up so we could finish it as quickly as possible. Well, that was a real challenge for the line following, and Griff spent probably more time than anything else tuning the PID controller and finding the right settings so that we could follow the line accurately. We should have a lot more time for it. Good lesson to learn there. If you're going to mess with a PID system, spend the time to tune it. Make sure you allocate it. The aiming system, originally we wanted to do an active aiming system. We wanted to find our target, computer vision, or some other direct measurement method. And we never had anything we were satisfied with, and for the money we could spend, computer vision wasn't going to work out very well. The complexity was increased. Will came up with a great idea. We could just do some math. We're going to figure out where we are on the board with geometry and trigonometry, and we're going to fire a dart. It ended up being far more accurate than we thought it was, and we abandoned color vision, or computer vision. Well, it turns out all the teams that were trying to use computer vision were all having problems seeing the targets. They were seeing fire alarm things on the walls next to it because they were red. Things weren't working well. We never had that problem. We never even thought about that problem. Good thing to know. And the last thing, the rules. Don't know why the IEEE competition rules changed. They change a lot. We went to the competition, we revisioned 3 of our rules, and 2 rule changes were made while we were driving to the competition. Need to keep your design flexible if you're going to do the IEEE project. Make sure you can adapt and go to the rule changes. We were able to do that. It ended up being fairly successful. So in summary, we were able to build an autonomous robot successfully designed, integrated, tested, and validated by ourselves. The project was just over budget after factoring in the spares kit and the course fabrication. Turns out the spares kit was very important. We shipped or popped a chip off a line sensor during testing at Kentucky. We were able to swap in our spare line sensor and keep going with just a little bit of calibration. And then we competed on March 14th, first technical competition rounds, as Joe told us, and ended up in 3rd overall. We do want to thank Mr. Knapp and Ms. Trez. Their help with logistics and supplies. Without that, we would not have done nearly as well. Also, you thank Dr. Askins. He eventually told us, stop, put it in a box, quit working on it. It was great advice. And we did very well as a result. I wish I could say it was a lessons learned for us, but we caught Griff tidying up wiring the other day. Any questions?
What rule changes?
They constantly changed the colors of paint, and they constantly changed how the rounds were going to be set up. The 2 changes that they changed while we were on the way there, the netting, they had netting over top. You saw from the video, it was kind of dim and hard to see because they had the safety netting over it. They changed the brand and color and kind of netting they were using at the very last minute. Most of the computer vision teams had a lot of hard times adapting to that. They also decided to take the final round from 8 schools to 4 schools. While on our way there, we were figuring all we had to do was get top 8. All of a sudden, we had to get top 4.
They also changed calibration.
Oh, that's right. I'm sorry. They changed the calibration rules on us, and we had to do a quick code change. That was on the way. That was about a week early. We thought we could calibrate when we got up there, and we couldn't. We had to hard code calibration, and we had to very quickly learn how to do EEPROM writes to the Arduino. We hadn't had to do it yet.
Lesson learned. Tell us about the Alabama, Mississippi State.
Yes.
I know all these department heads, so this is real good.
Oh, okay. So going into the final round, the top 4 teams who were going to compete, us, Evansville, Chattanooga, and originally it was University of Alabama. And University of Alabama, we were kind of talking to them. They were using a very similar firing method as we were, a very similar triangulation method. So we were talking to them a lot. And they were like, oh no, we're done, we're going to go drinking. There's no way we're in the final round. They'd done the math well before the points were tallied up and the results were posted. And then they were come up and said, well, we're top 4, there's no way. Then they found out Mississippi State was talking to the judges and trying to figure out why one of their darts wasn't being scored. They successfully made a dart, the judge didn't see it, and the camera system that the camera system that the judges were running was not working on that board when Mississippi State competed. They had no proof they made their dart. Alabama went, well, we've got video of our run, which was right next to Mississippi State's run, and we could see their dart go into their target during their run. So Alabama stepped up, said, hey, they made their dart, we can prove it. Mississippi State got into the final, Alabama had to recuse themselves. I thought that was very, very nice.
And they ended up winning.
Yes, and Mississippi State ended up winning overall in the final. Any other questions? Thank you.